Hello everyone, today we're gonna do an example question on calculating equilibrium constant. Okay, so for this situation we have to know the initial concentration and one of the equilibrium concentrations, and you're looking for the equilibrium constant. Okay, so you're looking for Kc. Okay, and then let's see how we're gonna deal with this situation. Okay, so for this example question, we have that the initial concentration. So let's put down the information we already know from here. So given is that initial concentration equals 2.5 of carbon monoxide, and then the initial concentration of H2 is 1. Okay, and then the other number we see is 780 degrees Celsius. Are we going to use this number for calculation? No, we are not. We don't need this number to do calculation. We don't need it to do calculation. Okay, this again for equilibrium constant is sensitive to temperature. Okay, so therefore we need to mention the temperature. However, you don't need it for the calculation. Okay, and then at equilibrium we have the concentration of carbon monoxide. So I'm gonna use EQ to represent that's the concentration at that equilibrium is 0.15, and then we're looking for the Kc. Okay, so let's see what we're gonna do. First of all, of course, let's start off from expressing equilibrium constant because that's something we're looking for, and see what do we need to calculate that. Okay, so Kc equilibrium constant equals to the product raised to is stoichiometric coefficient, the power of it, so it's gonna be CH3OH. Okay, so the coefficient over here is 1, and then we didn't write it out because again 1 we already know, so we just don't write it out. Okay, and then over the reactants raised to is the power of stoichiometric coefficient times the other reactants raised to the second power, because right over here the stoichiometric coefficient for hydrogen is 2. Okay, so this is expression for it. And then now let's see what do we know, what we don't know. Okay, so in this case we have the concentration of equilibrium. Okay, so let's give that subscript. Okay, so it's EQ, concentration at equilibrium, EQ and EQ. So we know that. We don't know the other two, so we don't know what's with this one and this one. So we need to calculate them based on the information we know. What are we gonna do? Okay, so for this situation we need to set up an ice table. Okay, so need ice table. Okay, so what's this ice table? That's, for me, I like to write out the equation first. Okay, so I'm gonna do this. 2H2 and give me CH3OH. Again, we understand that 1 mole of carbon monoxide reacting with 2 moles of H2 giving us 1 mole of CH3OH. Okay, and now let's draw the ice table. Okay, so the table will right over here. Okay, so ICE, that's our ice table. I stands for initial, C is change, E is equilibrium. And this is the table based off molarity. Okay, and then so again brackets represents molarity, concentration. Okay, so that's this table is about. Okay, now let's put down the information we already know. Okay, so we know initial concentration 0.5 and 0.15, and we know 1. Okay, and then again you go, well, we don't know the initial concentration of CH3OH. Do we know? I think we do, right? Yeah, because it's gonna be what? It's gonna be 0. Why is that? Because initially you only have carbon monoxide and hydrogen in your container, and then that means you have 0 of the product. Okay, so that's implied in this situation. Okay, and then now let's see. You know initial concentration of carbon monoxide, and you know the equilibrium concentration. So apparently we can calculate this difference. What's the change? Okay, so now I'm gonna do that real quick over here. Okay, so the change of CO, carbon monoxide concentration, will equals to what? The concentration of carbon monoxide at equilibrium minus the concentration initially. Okay, and then let's do the math real quick. Okay, so this will equals to 0.15 minus 0.5 give us, so it's negative 0.35. Okay, so it's negative 0.35 molarity, and then let's put that number into our table. Okay, so it's gonna be negative 0.35. Okay, again, for this reaction, we know direction goes towards which way? To the right, because your Q is gonna be bigger than Kc. Okay, so this is, in this situation, we kind of can predict. The reason for that, you have your container starting out, you only have reactants. Of course, the direction has go to forward direction. Okay, and then therefore your concentration of carbon monoxide is gonna go on. It's gonna decrease. Okay, and then the same way for the concentration of hydrogen is gonna decrease. And what's the rate is going to decrease? Okay, so the rate will be what? The concentration change of carbon monoxide, okay, to the ratio of the concentration of hydrogen change is going to be what? 1 to 2. Yes, it's going to be over here. We actually have a 1. We didn't have it out. Okay, so it's going to be 1 to 2 ratio. Okay, so that means every 1 mole of CO reacting with 2 moles of H2. So if you have 0.35 mole a molarity of CO reacted, that means you're gonna have double of the amount of H2 reacted. Okay, so this is very important for you to understand. Okay, so I'm gonna use this color. Okay, so you're gonna have two coming from where? The stoichiometric coefficient. Okay, 2 times negative 0.35. Okay, and then this turns out to be negative 0.70. Okay, so that's the the change of H2, and then what's at the end? Yes, it's gonna be 0.30. Okay, and then same logic, and then now what's over here? The coefficient for the product. So the product is 1. Okay, so it's 1 to 1 ratio if you talk about carbon monoxide. However, in this case, again, the concentration of methanol, CH3OH, is gonna increase. Okay, so the change is gonna be a positive 0.35, because you're consuming the reactants and produce the product, and the product is gonna be, the concentration is going to be increased. Okay, over here this number is going to be 0.35. Okay, so now we just found out what are the concentrations of each reactants and products at equilibrium. Okay, and then that's all we needed. Yes, now we just plug all those numbers back into our equation. Okay, so you will have the 0.35. On the denominator, you'll have 0.15 times 0.30. Don't forget that squared, that to the power of 2. Reason for that, again, because of this coefficient. Okay, so now do this calculation, the answer is going to be 26. Okay, so this is a situation, you know the initial concentration and one of the equilibrium concentration, and finding the equilibrium constant. Thank you for listening.